Alright, now after this introduction to non-abelian interactions, we can tackle the exciting topic of the standard model and what the fundamental interactions of nature are. For example, as we said before, as we said in the last lecture, there's this SU3 interactions of the color charges, and there's this electroweak sector of SU2 left times the hypercharged U1. And now let's focus first on the electroweak sector. The fermions that are we're gonna discuss first are leptons. It's Greek for light particles, essentially. And let us look at the fermion spinor psi that contains left and right-handed fields. And the left-handed fields are the electron neutrino. Let's talk for now about electrons first. The electron neutrino and the left-handed electron, and they're combined in this doublet where we replaced, before we talked about F1 and F2 here. Now F1 is the neutrino, F2 is the left-handed electron. They're combined in this doublet vector L of SU2 interactions, but this is the SU2L interaction where we have left-handed fields, that only left-handed fields being interacting with the electroweak gauge bosons. The right-handed fields don't feel them. The right-handed field is just the right-handed electron, and it's just alone. It's a so-called singlet R. The Lagrange has now the singlet combination R and the doublet kinetic term L bar D slash L. And then there is the gauge boson kinetic energy for the W's, and here the kinetic energy for the U1 sector, which we call B. Here we call the field B. We keep it deliberately not, call it deliberately not A, because it's not yet the photon that we observe. So the G field strength tensor has the abelian part plus the non-abelian part W cross W, and also we have the F mu part for the abelian part is just d mu B d nu B. As in the photon case, however, this is not the photon yet. Good, let's see how the covariant derivative acts on different fields. D mu on L is the derivative plus, here's the, let's call this strength G of this interaction, sigma W times L. This is the SU2 part. And there's also the 1/2 times the charge under the B field. And here the charge will be -1. We have to pick it. We pick it to a certain number, and as I show you, it needs to be this number to reproduce nature. And we call the strength of the interaction G prime, and then B is the U1 gauge field times L. This is the fermion here. For the right case, for the right-handed fermions, this second term here for the SU2 interactions is absent. The second term with the interactions with the U1 field is the same, just with the charge -2 instead of -1. Now let's have a look at the table of the charges. So the left-handed doublet is essentially the term that has two components under the SU2 field and interacts with the SU2 group. It has a so-called isospin quantum number. It has historic reasons why it's called like that. And the value of it is 1/2. And U1 charge, the so-called hypercharge Y, is -1. For the right-handed fields, there is just it's a singlet, doesn't interact with the SU2 charges. This has no isospin, and the hypercharge is -2. So if you look at it in components, basically this the projection of this third component of the isospin is +1/2 for the neutrino and -1/2 for the electron. It has to do with this angular momentum. It's very similar to angular momentum quantum numbers, actually. And that's why it's called isospin, even though it's an internal degree of freedom. It has nothing to do with the spin of the electron. Good. So what you have to know is the upper component isospin 3 is 1/2, and the third component of the electron is -1/2. Now, the electric charge, what we observe as electric charge, is a combination actually of this isospin third component and the hypercharge divided by 2. Well, because left-handed, now we can check for the left-handed electron, the hypercharge third component is negative minus 1/2, and y is minus 1, so we have minus 1/2 is total minus 1, which is consistent with the electron having negative 1 as electric charge. For the neutrino, we have minus 1/2 from the third isospin component, and minus 1/2 again from the hypercharge gives us 0. It's a neutral particle, doesn't couple to the electric field, and it's consistent with what a neutrino is. And the same for right-hand electrons. There is no isospin, so the minus 2 on 2 is just minus 1 for the hypercharge, and yeah, this is also consistent. The left and right-handed components of the electron should have the same charge. Now, it looks good so far, but we have no mass terms in the theory whatsoever. So we need to connect left and right-handed fermion fields to get a Dirac type mass. So if we write down a left-handed and a right-handed field here, L bar R, this is not okay. It's not, the indices, internally charged indexes don't match. This is a doublet of SU2, basically a two-component object, and this is a one-component object. We can't combine them in a meaningful way in Lagrangian, such that the total Lagrangian function is actually an invariant of the SU2 interaction. Yeah, this will basically, the symmetry, the SU2 symmetry, so to speak, forbids the mass terms for the fermions. Doesn't allow them at first glance. Also in this big high energy picture, so essentially this whole picture that we're discussing with the SU3, SU2 to cross U1, this is only valid at energies that are above the 100 giga electron volts, temperatures higher than 100 giga electron volts. And here, left-handed electron can be rotated freely in the neutrino, and nothing changes. This is really not what we observe at energies that are well below 100 GeV. So something has to happen here. Namely, the symmetry must be broken. Let's see how this actually happens. Let us introduce a SU2 and SU2 doublet scalar field phi. And now we can combine the L bar R with this. This is a singlet of SU2, but this is a SU2 doublet, so it's a vector of SU2, and this is a SU2 vector with two components. And then they can be dot product, like you can take a dot product of them into each other, and then you construct an SU2 invariant object. That's good. You can combine this. And then we know that this has hypercharge minus 2, this is a hypercharge plus 1 because there's a conjugation here. So that we have a hypercharge minus 1 in this term. It needs to compensate by another hypercharge from here. So we get a hypercharge plus 1 from here, which makes the whole thing again hypercharge neutral as well. So this is now a legit term for Lagrangian. However, phi is a scalar field. How would we make it into a mass term? This is a good question, and we have to introduce a new concept, called spontaneous symmetry breaking. Since we learned that the scalar fields can have those interaction terms with powers of phi, we can introduce the potential for this phi field, which has a phi squared term and phi to the 4 term. But the interesting thing is that the mass term, supposedly, has a negative sign here, which is a good indication that the theory will be non-stable, as I show you in a second. So if you draw this potential v of phi as a function of phi in the field space, you see that there's a maximum actually around where the phi field has essentially 0 occupation number, or is 0. It's not really a stable situation. So when the temperature drops, when the temperature is very high, it doesn't matter. So the field has energy and flies around somewhere high. But the temperature drops, eventually it's not energetically unfavorable to stay here around the 0 range. And then the field rolls down and settles in this in the minimum really, where its expectation, so-called expectation value, is non-zero, right? This has a value. let's call it V. And this is called the vacuum expectation value of the field, or VEV, and this will actually induce all the interesting physics that we see here. It namely, you could also say when the field here is at the center, the situation is symmetric, and when it goes down and chooses basically a direction, an offset from zero, and this breaks the symmetry spontaneously. It's called spontaneous symmetry breaking, SSB. Now, if you look at this field and components, there we have two components, and now let's make a choice for this vacuum state. The first component is 0, and the second component contains the VEF V. Now, if we combine it with the left-handed doublet and the right-handed singlet here, phi, you can write it also in components. You can write it as a vector, basically as a vector 0 V, and here we have neutrinos and electrons. Dotting it together gives us 0 for the neutrino term, but the VEF multiplies the electron term, electron left-handed, and then combining it with the right-handed component of the electron with a V that is just a constant number. So we are fine. We succeeded in writing down the mass term, where the mass is actually the Yukawa coupling. This is the called Yukawa coupling between the two fermions fields and the Higgs field. This, by the way, it's the famous Higgs field, suggested by Peter Higgs. And the mass term for the electron is the Yukawa coupling of the electron times the VEF of the Higgs field, but neutrino remains in this scenario massless. Finally, nature has 3 generations, 3 copies of the same leptons, but with different couplings to the Higgs field, different Yukawas, and that gives them different mass. So while the electron has a mass of about 511 kilo-electron-volts, like half a mega-electron-volt, the muon, the next heavier lepton, has about 100 MeV mass, and the tau lepton is really heavy and has more than 2 GeV in mass. Almost 2 GeV in mass. And this vacuum expectation value V is at 246 giga-electron-volts, so it's actually a pretty large number, and all the leptons have quite small Yukawa couplings. The situation is similar with quarks, particles that carry the strong color charge, but they also carry the left-handed fields carry also the electroweak charges. So you can write them down into, well, intuitively you could call the upper component up component and the down component down left. And you could also say you have U and D right-handed components, but they are not arranged in the doublet structure. They don't feel the SU2 left-handed weak force. Now observe the difference to the lepton case, that we now really have a right-handed down type, down type, and the right-handed up type field. For the electrons, we only had the one type of down type field, basically the electron right-handed, no right-handed neutrino. We have not written down the right-handed neutrino term. So the quantum numbers are -1/2 for the isospin. Sorry, this actually is just 1/2 for the isospin, and for the Q, L is the doublet field, is a doublet, and it has hypercharge 1/3, and the UR and DR are singlets under SU2. They have no isospin and have hypercharges of 4/3 and -2/3. So combining them, again, we use this isospin third component plus 1 plus y on 2, the hypercharge divided by 2. So for the UL, the left-handed up type field, we have 1/2 for the isospin third component plus 1/2 times 1/3. If 4/6, it gives us 4/6, which is plus 2/3, which is the correct electric charge for the up-type quark. For the down-type left-handed field, we have -1/2 from the third isospin component plus 1/2 times 1/3. 1/3 for the hypercharge gives us -2/6 when we go to the same denominator, but that can be simplified to -1/3, which is correct for the down-type quark charge. For the right-handed fields, it's simpler. We don't have isospin, but we have 1/2 times 4/3 plus 2/3, or -1/2 times -2/3 is -1/3, which is the correct charge again for the down type right-handed quarks, or for the down type quarks. So this is good. And the mass term with the Higgs field has now two terms. You cover Y type, up type quarks with phi dagger Q bar L multiplying UR, and then we have down type quark terms where we have just the Higgs field phi Q left bar dr. Writing it in components, this dagger flips the Higgs field, so we have V0 here, which in this combination gives us the mass for the up type quarks U bar left UR here with the U cover YU, and this here gives us the mass for the down type quarks GL bar dr. GL bar dr. Here we have a defined down type field mass term. Okay, so again we have three generations of quarks. The MU, the mass of the up type quark of the latest generation, is just 2 MeV. The down type quark has about 5 MeV. Then the next heavier generation of charm, so-called charm and strange quarks, has about a GeV and about 100 MeV masses. And then the really heavy ones for the third generation, the top quark, the heaviest one, has 173 GeV. This is a really heavy particle, the heaviest particle we know, and the bottom type quark, which has 4.2 GeV mass. So this is the mass content of the 6 quarks that we know, and these 6 quarks essentially have all 3 color charges, so you could think them up in terms of having red, green, and blue charges. So we would have actually 6 times 3, like 18 fields in a way. Good. So the quarks also carry this SU3 color charge. They are basically a triplet, and they interact with the gluons, as we said above. But at energies that are lower than 100 MeV, or temperatures that are lower at 100 MeV, which is most of the stuff we observe in nature, we don't see that. The running of this coupling, as we discussed running, at low energies grows. The coupling, the strong interaction coupling alpha grows and becomes larger 1 at energies below 100 MeV. The theory is strongly coupled that forces actually quarks to undergo so-called confinement, and they need to hide their color in color neutral states. That could be, for example, a meson, where we have a QQ bar having, for example, an anti-red and red color that makes it a neutral object, or baryons, which means heavy particle in Greek. So we have 3 different quarks of the red, green, and blue type. This also makes the whole object color neutral. And as example for the lightest particles in this situation is U bar U combination or D bar D combination. It gives us the neutral meson. Lightest meson is called the pion. And then you have a U bar D, which is a pi minus, or a U D bar, a pi plus. So we have different light fields. So they're so-called pion fields around 100 MeV in their masses. And the combination of UUD, which 2/3, 2/3 minus 1/3 charge, gives us a +1 charged particle. This is a proton. And we have a combination of 2/3 minus 1/3 minus 1/3 from UDD, which is a charge neutral contribution combination, and it's a neutral. It's a neutron. Their masses here are around the GeV of those particles, and those particles have also spin 1/2. They're fermions, while the combinations here for the mesons are spin 0 particles. They're bosons. And we actually have an effective theory that describes interactions of those protons with the mesons, for example with the pions. And the pions act actually as force carriers, keeping the protons bound inside the nuclei, and neutrons as well. And this is the force, the pion force, that acts on those nucleons, on the protons and neutrons. It's a strong nuclear force, or a description of a strong nuclear force that keeps nuclei together. For example, a charged Q nucleus, Q equals 2 nucleus, 2 protons and 2 neutrons, can be combined into helium-4. Despite electric interactions of protons repelling each other, the strong force at short distances overpowers them by far and keeps them together. but the range is quite limited. So since the masses of the pions are around 100 MeV, their range is about like 1 Fermi, 1 femtometer in distance. Those distances, they are far stronger than the electric charges, but at larger distances, this force quickly disappears, and the only thing that remains is the electric charge of the nucleus. Good. But now, since we're talking already about electromagnetism, let's talk about how the Higgs mechanism is actually affecting the gauge boson sector. Yeah? How does this spontaneous symmetry breaking affect the gauge boson sector? Let us look at the covariant derivative acting on the Higgs field. It has this SU2 part and this G prime hypercharge 1 term acting with a B field acting on phi. And let us just input this vacuum expectation value as we had here in this derivative term. So this gives us the derivative vanishes, vacuum expectation value is quite constant, so the derivative of it vanishes. And now we have from these terms contributions that have Wi and W2 contributions from this sigma matrix is multiplying the two-component field here, just picking up the lower components. And then we have from this B field only the only comes into the lower component, and is another combination here with a V. So the kinetic term is this d mu phi dagger d mu phi. When you write it out, we get three combinations that look like mass. Basically, W1 squared, W2 squared with a prefactor that is proportional to the VF squared, and a combination GW3 minus G prime B squared times this prefactor. Those are the mass terms that give mass to gauge bosons. But now we can make a basis rotation, namely define new fields that are called Z and A, that are a linear combination of W and B fields. So for example here, this W3 minus some constant times B mu, that is here, essentially will be the field that has a mass. So in the end of the day, this Z term, Z squared term, when we write this expression here after the rotation, the W1, W2 mass terms are still the same, but the this mass term here is a mass term for a new object that we call the Z boson, which is a superposition, linear superposition of the W3 and B fields, the hypercharged field and the third component of the electroweak fields. And their mass terms are related. Those are equal. Those will be the W plus and minus gauge bosons. And this one has no electric charge, but it has a mass term that is related to these ones, while the MW is the square root of this factor times 2 is essentially G times V over square root of 2 is 80 GeV. Given that this is 246 GeV, we know that this has to be 80 GeV, and Mz is Mw, the same term here, divided by this cos theta. This is called the Weinberg angle, and it's related to the relative strength of the G and G prime couplings. And so this is the rotation angle, so it has to be smaller than 1. So you divide by a number smaller 1, you get a larger mass. So the Z boson is somewhat heavier than the W boson at 91 GeV. However, there is also a combination for a field that is essentially A B mu plus G prime W3. You see, this is the orthogonal combination to this combination that we call the Z field that gets a mass. This combination of the B hypercharge and the third component of the isospin is we call A, and it remains massless. So there is no mass term in this gauge, in this kinetic term that appears from it. And that means that this is the massless long-range field that we have, and this is the photon of electromagnetism in our nature. So now we found that strong force confinement holds nuclei together, and that the photon is a long-range force that can bind the leptons to the nuclei, the charged leptons. Yeah, so the electrons are bound, for example, here to this helium-2 nuclei, needs two electrons, and it will form a neutral atom with Q equal to 0. Now, what are actually the W and Z bosons good for? They have a coupling that is alpha weak, defined as G2 squared over 4 pi, which is 1 over 29, or roughly 1/30th. So it's about 3 times stronger than the electromagnetic coupling, 1 divided by 137. But their large mass makes the interaction very weak. So their distances are really operating efficiently only on the sub-Fermi scale. And what they do is essentially they flip SU2 components from one to another. What does it mean in practice? If you have neutron with UDD quarks, yeah, 2/3, -1/3, -1/3 in charge, when they emit a W minus, they flip from this -1/3 down type quark into an +2/3 up type quark. The charge is conserved, yeah, you go from -1/3 to +2/3 and emit a -1 charge here, so the charge in the vertex is confirmed. W's immediately decay since they're quite heavy, a lot of energy access is here, and in this process there's not enough energy to produce a real W, so you have to produce a virtual basically W, and that suppresses this reaction rate very strongly. And so this W then decays into an electron plus an electron antineutrino, and you have, like, the electron has a negative charge, -1, and the proton now returned essentially by turning this UDD into UDU, right, state that is has a positive charge +1. So the total charge is conserved. We have a +1 object, a -1 object, and the proton and electron are now the two things that come out, and the neutrino flies away as well here. And yeah, this process is essentially called beta decay. A neutron goes to proton plus electron antineutrino, and it has been observed for a long time and postulated. I mean, the neutrino was postulated by Pauli, saying that it's needed to conserve momentum, for example. And for a long time, it was thought that those neutrinos, as predicted by this kind of structures that we just discussed, are actually massless. But this is, as I tell you in a second, is not really the case. Let us just dream of things that could lie actually beyond the standard model structure. One beautiful fact about the standard model is that the quantum numbers could be embedded in something larger. Okay, like abstractly, like me write this in this way to say, okay, you could think of fermion multiplets that are 5 and 10, you know, or better to say 5 bar and 10. And the symmetry is then SU5, the total symmetry of the theory. And that is the only force, the only that acts and contains all the other forces as sub-elements. But all the fact that it works has to do with the possibility of embedding the SU3 times SU2, SU3 times SU2 times U1 structure is completely contained in the SU5 group. This is a group theory fact. And the general number of generators of the SU5, as we said, is n squared minus 1 for n equals to 5 is 24. So actually, and it contains all 8 gluons. It contains the 3 W and Z bosons and the photon. So this is fine, right, with 12 fields, but there are 12 other fields that are not accounted for, so there are actually lots more gauge bosons, so like 12 more gauge bosons. And let's look at the structure of the 5 and 10 representation of the SU5 group. It can take, in this way, the right-handed down type quarks, right? Okay, 1, 2, 3 stand for color. So these 3 types, the right-handed down type quark live in this 5 plet. And the doublet of leptons, the left-handed electron and the neutrino live in the two remaining components of the 5-bar fermion multiplet. And the 10-plet is essentially this matrix representation, which has the lepton doublet, the quark left-handed doublet with up-type and down-type quarks with 3 components in this block. So it's a 3 times 2 block. Then this has the right-handed field of the electrons sitting here in this 2 by 2 block that is related by symmetry. So it's just one fermion field that lives in here. This is also related by symmetry here, but independent components live in this 3 by 3 subblock, which are independent of those, but they're mutually connected by symmetries. So there are three more fields, which is just right-handed up-type quarks that live in this block essentially, which is very beautiful because you have multiplets of matter that unify the fields, not in one, but at least in just only 2 representations. It's less than the it's less than this 1, 2, 3, 4, 5 different multiplets of the standard model. So it's already a little bit more elegant. And the main thing is that all the forces are replaced by one force that one would call it at the energy where this theory is operating, just the SU5 force. Now, what does it predict? As I said, there are many more gauge bosons. It looks pretty, but the new gauge bosons do something interesting, and namely they can take, if you have for example, here we have a proton here, d with normal arrows, goes like this. But now this new gauge boson can turn 2 U quarks into or coupled to 2 U quarks in such a way that it then decays into an electron and the down-type quark. And this is something that does not happen in the standard model because the electrons and down and quarks live in different matter multiplets. But here, you can imagine that the gauge boson rotates components from here to here or from here to here, and really allows this transition from, like, the electron can turn into a neutrino when it interacts with the W here. We can turn essentially the quark into a lepton, into an electron, or the X gauge boson decays into a lepton plus quark. This is something that is not possible in the standard model. And it allows the proton to decay to an electron and a pion. The bar combine to a pion, pi 0, so you have like P plus goes to pi 0 plus a positron, E plus. Well, this is not observed in nature. Protons are enormously long-lived. That means that and there are big experiments looking for those processes actually, but that means that the mass of this X gauge boson here to make this lifetime so long has to be larger than 10 to the 16 GeV. Well, this sounds very high, very energetic, very high mass, but the running of these couplings GS, G and G prime actually suggests that they meet somewhere to become a G5. If they actually become a SU5 force, they meet somewhere around those large scales of 10 to the 16 GeV if we just do this theoretical extrapolation. So it doesn't seem too inconsistent, this fact that we haven't seen the proton decay, just because the scale of this violation of the baryon number basically is so high, which is also good, because if our protons in our bodies would decay too fast, we would just all kind of disintegrate without a chance to have a fair evolution and whatever. No really interesting matter will be present in the universe, because again, the pions can decay to photons, so in the end of the day, all the baryons would eventually turn, while let's say the weak decays from N to P, and when this is too fast, the P's would decay into pions that go to photons and to electrons. So we just have a universe full of leptons, which is boring. I mean, if those here would even annihilate further into, if those two would annihilate further into into photons with other leptons, so we would really end up with a universe filled with only photons, which is quite terrible. Anyway, luckily this mx seems to be quite heavy, and these protons are stable, we have matter, this is good. But this is an interesting thing to search for, and there are ongoing experiments like so-called super Kamiokande experiment and others that look for this process. Finally, there are other things to think about. For example, neutrinos are light, but they have mass maybe at the eV scale, maybe somewhat below. We see it because of flavor oscillations between different neutrino flavors. And this is a big topic, how to introduce masses to neutrinos. It's a topic of physics beyond the standard model, which, for example, requires at least the existence of a right-handed neutrino or another field that would allow to have a term that is something like nu r, nu left, nu r. Or maybe there's this so-called Majorana type of interactions that allow a mass term. But this requires also additional physics that violates the so-called lepton number and allows a neutrinoless, so-called neutrinoless double beta decay. Two neutrons turning into two protons without emission of neutrinos, just emitting electrons. This is a very rare decay that hasn't been observed and is being actively searched for actually. So then also the standard model doesn't have a candidate particle for dark matter that is responsible for structure formation in the universe and is very important to reproduce the rotation curves of galaxies and other phenomena in the universe. And neutrinos cannot explain this. They're too light. The particle has to be heavier than neutrinos or produced in a way that it's not thermally coupled to the standard model. Anyway, there's complications, but neutrinos cannot explain the dark matter, even though if they interact weakly with other stuff. And we need another rather weakly interacting particle, or maybe another type of matter that would allow us to have some sort of non-visible substance or rarely or weakly interacting substance that is massive. It does not, it does not seem to exist in the standard model. Finally, the standard model cannot explain the matter-antimatter asymmetry, essentially that we have more to a roughly like 1 to 10 to the 9 ratio in terms of let's say 1 to 10 to the minus 9 excess of matter over antimatter, which is small, but still significant enough to have all the structure of matter in the universe. And having that, this asymmetry needs to be generated somehow in a so-called baryogenesis scenario in the early universe. So we don't know how it worked, but it must have happened in order to have our matter not being annihilated by antimatter. So there must be some physics beyond the standard model, because the standard model itself does not have enough baryon number violation, essentially. So this is not there, and we are looking for answers how this baryon number can actually be violated, and the baryon asymmetry and lepton asymmetry can be generated from it. So overall, there is a rich menu of open questions beyond the standard model physics, which is quite exciting and an old and mature field, but still it contains a lot of open questions, in particular with connection to with astrophysics and astroparticle physics. Exciting results are expected to be found. Thank you. That was the entire course of quantum field theory, including the introduction to standard model and some dreams and thoughts on the beyond the standard model scenarios that we could have.